Okay, welcome everyone to our CASI Ottawa branch event. I would like to welcome my co-host, Professor Catherine Mavericks, who's a full professor of mechanical engineering at the University of Ottawa. Her specialty is in numerical methods for aerodynamic simulations, and she's also NSERC chair for women in science and engineering since 2011. And it is my great pleasure to introduce Kelsey Doerksen, who I've known since I think about 2016 when she was at Carleton and involved with the Mars Rover project. She is a space systems engineer in satellite operations at Planet, where she operates the world's largest Earth observation satellite constellation. She holds a bachelor's degree in aerospace engineering, space systems design from Carleton University, and a master's in electrical and computer engineering from the University of Western Ontario. Kelsey has previously worked at the NASA Jet Propulsion Lab, or JPL, on machine learning and instrument autonomy and the instrument autonomy team, developing machine learning solutions for future Mars rover missions. And researches with Paris Observatory on the impact of space weather and space debris to our atmosphere and spacecraft orbits. She's an incoming PhD student at the University of Oxford's Autonomous Intelligent Machines and Systems doctoral training program, where she will be focusing her research on utilizing machine learning and Earth observation imagery to quantify impacts of climate change. And the title of her talk is A Canadian's Journey to a Career in Space, from developing a Mars rover technology to operating the world's largest Earth observation satellite constellation. So this is going to be very exciting. And if you have any questions during the talk, please use the chat function to ask them, and raise your hand, and we'll try to have most of the Q&A at the end. But if it's a very compelling question, then you can just interject right away. And my name is Omar Majid. I'm a co-host of this meeting, and I'm a systems engineer with MDS Aero Support. So, other items of business. The talk should take about 30 to 45 minutes. And then we'll reserve the time left over for Q&A at the end. And without further ado, Kelsey, thank you so much for volunteering to give your presentation. And I'll let you take it from here.
Awesome, thanks, Omar. I'll share my screen here. Can you see that okay? Is it good size and everything? Awesome. Thank you so much for the introduction, and thank you, Cassie, for inviting me to come talk a little bit about my journey and the different projects I've been able to work on. I'll just jump right into it. I'll try my best to get through it with enough time for questions, because I always like kind of interacting with people that want to listen to me talk. So just get right into it. Omar's given a really great overview, but these are kind of the different hats that I'm currently wearing right now. So I'm a satellite operator at Planet, based in San Francisco, California, and I've been at Planet since February of 2020. I also research with the Paris Observatory on space weather impacts on orbital trajectories of satellites as well as space debris. For those of you who are familiar with the Space Generation Advisory Council, I'm the manager for the Space Generation Congress this year as well. I also do some freelance career and academic consulting. So I try to help people out with applying to different jobs, particularly in the space sector. And I'm starting my PhD at the University of Oxford this fall in the Autonomous Intelligent Machines and Systems program. So that's just kind of a little bit about me. But I wanted to include this slide to give kind of an overview of a very brief timeline, I guess, of my career thus far, and really to highlight the fact that no path is linear, and mine has been anything but linear. So I've just highlighted a few of the things that to me really have stuck out in my journey and have gotten me to where I am today. So I have graduated from the University or Carleton University's Aerospace Engineering program in April of 2017. And that summer, actually, I spent the summer in Newfoundland and Labrador teaching science outreach with Dalhousie University, which was a really great experience. And I strongly encourage anyone, within the STEM fields to give back through outreach. It's a really rewarding experience. And that September, I began my master's program in electrical engineering at Carleton. But I felt honestly pretty lost that first semester. I wasn't really passionate about what I was researching. I didn't feel that I had a strong enough tie to the space field. I wasn't honestly happy in the program. I loved Carleton, but I just felt like this wasn't kind of the right place for me for my master's program. And so I decided to kind of make the switch and take the leap of faith really to join Western University's electrical and computer engineering program. And I guess technically dropped out of Carleton my master's and joined Western's program there. So that was kind of the first big bump in the road of my, initially I had what I thought was a really clear path forward, but I ended up switching my master's one semester in. But I had a fantastic time during my master's program, and the first summer at my master's, I was able to live in Paris and work at the Paris Observatory studying space weather and space debris. And this was honestly totally unrelated to my master's thesis, but I had somehow convinced my supervisor to let me spend the summer in France researching something totally unrelated to my master's thesis. And that summer had really set me up for where I am today, because I still research with the Paris Observatory and I have fantastic relationships with them there. So I'm really thankful for that opportunity. And then when I got back in August 2018, I switched my thesis for the third time, probably since I started my master's journey. And between August 2018 and 2019, a lot happened, but the highlight reel really is that I was able to successfully defend and pass my thesis defense and graduate from Western University. And immediately following that, I think it was honestly 2 days after I defended my thesis, I moved to Pasadena in California and started my internship at the NASA Jet Propulsion Lab in the Machine Learning and Instrument Autonomy group. That was from October to December of that year. And right after that, I made the full plunge to moving to San Francisco and joined Planet full-time as a space systems engineer. And that's kind of where I am today. So these are really just kind of the highlights of different things that I've been able to do and the opportunities I've had over the past few years. And really, I wanted to share it because I think, if anything, I hope folks would take away that are, especially those that are early in their career like myself, is really just jump at any and every opportunity you can, because you never know where it will lead you. And I'm really thankful for the position I'm in today. And I definitely wouldn't be where I am if I hadn't have, taken these kind of side quests, I guess, on my journey to be in the space industry. But I want to talk about two specific kind of projects, or I guess my experiences in the space industry on two specific places. So the first will be at the NASA Jet Propulsion Lab. And then I also want to talk about my work at Planet. And specifically, we had our most recent launch in January 24th, 2021. And so I'm going to be actually sharing with CASI and all of you today kind of the first look at the results from our commissioning campaign. So this has never been shared, which is really cool. But I did get it approved for my security team at Planet, so I won't get in trouble. But first, I want to start off with my work that I did at the NASA Jet Propulsion Lab. So to set the stage on the purpose of my internship and the purpose of the work that I was doing here, so what I did was machine learning for Mars rover technology. But I first wanted to kind of give you a little anecdote or a use case as to why this was really important. So I'm sure many of you are familiar, but for those of you who are not, the Mars exploration rover Spirit was one of the two twin rovers with Spirit and Opportunity mission from the NASA Jet Propulsion Lab. And on March 22nd, 2010, unfortunately, this mission ended prematurely because the rover wheel actually got stuck in the Mars regolith. So you can see on that animation on the right side of the screen, those are images, and you can see the wheel there is actually stuck in the Mars regolith. So currently, rovers rely only on sight alone to navigate, and this presents a really significant limitation because we can't determine what the actual soil properties or thermomechanical properties of the regolith are just from an image alone. So a high level of the concept of operations of a rover and the rover team is pictures are sent back to the rover operators, who then will analyze the images to determine the best path forward. But visuals provide incomplete information because they require operators to guess terrain features, and it also relies on a manual input from the operators at all times for navigation. So that will also result in slowing the rover's progress, and it also limits the ability to navigate independently. So my role at the Jet Propulsion Lab and the project I was working on was how to figure out a way where we could allow the rovers to be more intelligent and more thoughtful in when they're traversing, so that we don't have these things happening again in the future. And we did that with what we call the Barefoot Rover project. So the Barefoot Rover project is a wheel concept that enables the rover to essentially feel the terrain it's traveling across. So using a 2D pressure grid of sensors, which is this yellow part here of the wheel you can see on the screen, and an electrochemical sensor, the wheel actually senses features about the terrain. So we use it for a wide variety of applications. We can use it for determining hydration of the regolith, for anomaly detection, to assist with rover safety and stability, to be able to determine if the wheel is slipping or the relative sink coefficient, and that was what I was working on. Terrain classification, so determining whether or not the regolith is very fine grained, if it's more coarse grained. We also use it for subsurface rock detection and just a variety of other thermomechanical properties. So I was really fortunate in that my project, or my role on this project, was I got to actually build the rover wheel. I then collected the data. So we had essentially these big troughs where we would roll the wheel over. It was connected to kind of this robotic chassis, and it would roll over the different types of materials so that we could essentially gather the data to train our classifier. I then worked on the feature analysis. So we collected a ton of data, and I was using Python, which I'm sure a lot of you are familiar with, and different ways that we could automatically extract hundreds and almost actually thousands of features from this kind of time series data to be able to train a machine learning algorithm. And then I also got to work on the actual machine learning portion where we were training a random forest regressor to be able to predict slip at any point in time. One really cool image I wanted to include was showing how the Barefoot rover actually sees what it's rolling on top of. So this figure is a graph showing the pixel values, showing the wheel rolling over the sand where we wrote JPL written in the sand underneath it, and I can actually see that pattern. So I thought that was really, really cool. So essentially what happens is with machine learning, it can analyze the interaction between the wheel and the surface. And again, at JPL, my objective was to work on the predictive wheel slippage and sinkage use case. So for those of you who maybe are confused with what wheel slip is, it's really quite simple. It occurs when the force applied to a tire exceeds the traction available to that tire. So I'm sure for those of you connecting from Ottawa or anywhere where there is a Canadian winter or winter at all, you've probably experienced when you're driving a car and you can feel your car kind of slipping on the ice. That's essentially what we're trying to avoid with Mars rovers when they're on Mars. So under different terrain conditions, wheels will have different slip and sink ratios. And so this is why we are training it on different types of soils. So to give a little bit more detail, but I don't want to get too technical, and I'll have time for questions more about it at the end. So as the wheel moves across different terrains, it creates a time series of pixel values from the pressure sensors. And the time series data was then used in a random forest regression algorithm to be able to predict the wheel slippage over time. So really at a high level overview, we would roll the wheel over different types of terrain. We would collect that data. We would then apply the machine learning algorithm, and it would output a slip prediction. So the idea or the goal would be able to have this slip prediction as a warning system for the rover, and this would actually be on board future Mars rover technologies and future Mars rover missions, so that once a specific slip threshold has been reached, the rover is then alerted and can autonomously recognize that it's at high risk of becoming stuck in any sort of Mars or lunar regolith and should move backward in the direction that it just came from. And then it can then reassess with operator intervention. So the goal was really to make the rover almost smarter and be able to infer the different terrain it was rolling across. And then that way we don't have to have situations where we're having to mitigate for things happen. We can actually have the rover be smart enough to make decisions so that it doesn't get stuck or damage its wheels or anything like that. So with that, I want to jump into now something a little different, which is satellite operations at Planet. Go to my next slide here. Hopefully this can play okay. Great. So this is a really cool animation of our Dove constellation. So I operate the Dove constellation at Planet, which is hundreds of CubeSats that are in the sun synchronous orbit, covering the entire Earth's landmass every single day. So since its inception in 2010, Planet has launched over 400 Earth imaging satellites with the mission to provide coverage of the entire Earth's landmass at a daily cadence. And at Planet, we aim to use space to help life on Earth, which is one of the reasons why I wanted to join Planet, where I'm able to really feel the impact that I'm doing in the space industry, and really specifically to the impact that it's having on our planet. And we're able to do that through providing Earth imagery with our Dove, Super Dove, and SkySat satellites. So Planet's mission is dedicated to imaging the entire Earth every day, and through that, we're able to enable global visible change to be accessible and actionable. And so pictured here, or I guess animated here, is our Dove constellation of satellites, which are CubeSat satellites. Oh, I'll just replay. We have hundreds of Doves that work together to achieve our mission, and I'm really lucky to be one of the 9 operators that work on the Dove constellation. So it relies on a lot of automation, and we actually are starting to implement machine learning into our operations as well, which I will talk about in the coming slides, because again, we have hundreds of satellites and there's only 9 operators. We have 2 distinct satellite operations teams. One is in Berlin, which has 3 operators, and the other is in San Francisco, which has 4, and then we have our 2 respective managers as well. So I'll go to perfect. But Planet just doesn't have satellites. We also have a really extensive ground station network as well across the globe. We actually have one in Inuvik, which I think is always cool to see. So these are just some high-level stats of the different sort of metrics related to, what Planet can do and the different things that we do. So we've had over 452 satellite deployments from 10 rocket types in 10 sites in 7 countries. So we have a really I don't love the word aggressive, but aggressive procurement strategy for launches, in that we try to launch essentially anywhere in the world that we can. So instead of being limited to Cape Canaveral, for example, we also launch from New Zealand or even French Guiana, different regions across the world, so that we can get our satellites up as fast as possible. We've had 100% successful first contact rate, which basically means once we've deployed a satellite from either the rocket or even the ISS, which we used to do back in the day, we have a 100% successful rate of getting that first contact with them. So that's really exciting. We've had 30 successful launches. We downlink 25 terabyte of data a day, which is a ton of data. And a lot of this is imagery, but we also downlink, of course, a lot of spacecraft health telemetry to be able to, gain insights into the health and productivity of our satellites. And on average, we take about 1,300 images for every point on the Earth's landmass every single day. So we have a lot of pictures, a lot of satellites, and a very small team, which was one of, honestly, the really exciting things about working at Planet, is because there's no such thing as busy work in satellite operations at Planet, especially when there's such a small team. So you know right away that the work that you're doing is extremely impactful to the company's success, and just you're physically operating satellites every day, which is really cool, and something I definitely had to get used to. I remember being really afraid the first time I sent a command to space and thought I was going to break something. Luckily I didn't, and I haven't yet, knock on wood. But yeah, it's a really exciting company to work for, and just in general, being able to be a satellite operator is an incredibly exciting job, because there's just always something new every day, and kind of a new problem to investigate. To give you kind of a high-level overview of what, how the concept of operations, or how we operate satellites. Essentially, this is kind of a quick explanation. We don't take any images over the ocean or over the open ocean. We do imagery over ports, which might be of interest. We do a lot of work, or we have a lot of use cases related to identifying illegal fishing for some of our customers. So things related to ports or main infrastructure surrounding land in the ocean we take images of, but we don't take pictures just of the open ocean. So we're always imaging over land. We use X-band for our data downlink, and we also use LST and S-band for communications with our ground stations as well. And we do things like this for high-speed downlink is normally used for things like pictures, and then things like low speed would be for things like health and spacecraft telemetry. We also run a variety of maintenance activities. So these are things like file system checkouts to make sure that our satellites are healthy, that there's nothing going wrong with them. We do these on a monthly basis, but some of them we do even on a quicker cadence. And these are also scheduled autonomously, which is really nice. So we don't have to have an operator, oh shoot, I forgot to run this type of maintenance activity this month. We have that automatically set up. So that's really nice as well. And to kind of give you an overview of like the day in the life of what my job is, it changes definitely every single day. But these are sort of the 5 main areas of work that I do on a daily basis. So I develop and enhance automation tools. So what that means is we rely on a ton of automation in our operations because we have so many satellites and so few people working on them. Luckily with planets, the way the planet is set up is that our Dove constellation is made up of CubeSats. We have very similar hardware between our launches. So that way we can make one automation tool and it can apply to hundreds of satellites at a time, which is really nice. I also work on a lot of data analytics, and I utilize metrics for data analysis to assess the satellite performance and health. So I mentioned before, we get tons of data down from our satellites every single day, and that includes the health data related to all the different telemetry channels. So you can think about any sort of subsystem on a spacecraft, whether that be power, thermal, related to the CPU. We get all of that telemetry down from every single spacecraft. And again, we have hundreds. So we have to really do a lot of data analysis to be able to aggregate all that data, clean it up, and be able to make informed decisions as to whether or not satellites are performing as expected. And a part of that is also developing and enhancing scripts to aggregate satellite data into metrics. So I do a lot of Python programming, I'm really lucky in that I feel that my job as an operator utilizes a lot of my aerospace engineering and specifically my space systems design, education, but as well as that, I definitely needed my computer engineering degree to, be a strong programmer, specifically in the role that I'm in. We also perform daily check-ins on the fleet. So how it works is one operator will be responsible for a full check-in on the entire fleet every single day. And it changes each week who's responsible for that. So it usually takes about 1 to 2 hours, which when, again, you consider hundreds of satellites and only a single person, like that's pretty good. Depending on the day too, it could be, quieter in space, which is always nice, and take a little bit less time. But we rely on these, different metrics that we've aggregated and automation tools to help assist with this daily check-in so that we can really assess the satellites at a high level and see if there's any sort of anomalies or anything going on, and then deep dive into that following the check-in. And of course, a lot of my work is identifying, triaging, and root causing and resolving, hopefully, satellite anomalies. So this is on the daily, but it's something that's really exciting part of my job. Definitely, again, there is no such thing as busy work at Planet for sure, and definitely not in satellite operations, but it's part of what's really exciting. And I'm really thankful for that I get to kind of debug satellites on a daily basis. So with the interest of time, one thing I wanted to focus on part of satellite operations was our latest commissioning campaign, which was Flock 4S. So we launch all of our satellites in groups, and we call them flocks because our satellites are doves. So the most recent launch was our Flock 4S or F4S satellite launch. We had 48 satellites a part of this launch on January 24th, 2021. It was part of SpaceX's Transporter 1 mission. That is a animation there of the launch itself. So the way our deployment worked, because I will refer to some I guess, like high level metrics about it. So just to give you an idea, is 40 of the satellites were immediately deployed after launch. And then we had another 8 satellites with in an ion deployer, or a part of Deorbit, which is a space company we work with. And they would deploy 1 satellite every 2 days. And that's starting with 2 weeks after the launch date. So the reason why we did this is to help out with spacing or phasing between the satellites. And luckily, I was fortunate enough to be one of the campaign leads. So myself from the San Francisco team and my colleague Stefan from the Berlin team, we were able to be the satellite operators that were leading this commissioning campaign. So essentially what that means is we were responsible for planning out, when commissioning would start, with in terms of, we deploy 40 at once. Are we going to start commissioning all 40 satellites at a single time? We were responsible for working with all the different sub teams on what was needed before the launch happened, what sub teams would be scheduling for what operator would be responsible for the satellites on which day, actually working on some of the automation tools and getting those things done so that we could have that deployed and ready for to be implemented into this commissioning campaign. And this was one of our most successful and our most autonomous commissioning campaigns we've ever had, which was really exciting. And both Stefan and I are only a year into Planet at the time that we got to lead this commissioning campaign, which I think is pretty astounding, honestly, for someone just early in their career. And again, kind of why I'm like very pro startup, but I also work at one, so maybe I'm biased, but we were really fortunate to be co-leading this, and it was really exciting and a really cool opportunity, definitely. To give you an idea of what commissioning actually is, or at least what the satellite operations team is responsible for in commissioning. When I mean commissioning, I am talking specifically about from as soon as we launch the satellite and deploy it until it's able to start imaging. So there's other different commissionings or commissioning processes, like for our specific camera, we have a camera team that does their commissioning, but I'm focusing just on what the satellite operations team is responsible for. So there's really 5 different stages to commissioning. The first is establishing initial contact with our satellites and gathering health telemetry and making sure we've, that the satellites we launched, we can actually communicate with. So I mentioned before that we have a 100% success rate, and luckily when I was leading it, we didn't mess up. So we still have a 100% success rate, which was very good. The second part of our commissioning procedure is detumbling our satellites. So our satellites are tumbling when they're deployed from the rocket. So we detumble them using magnet torquers and making sure that they're spinning at a safe rate. We then deploy our solar panels and we activate burn wires to enfold the solar arrays on our spacecraft. And I should mention this is specific to Dove commissioning, so our CubeSat, Dove and Super Dove, and not SkySat. That's not the team I work on, so just to as a little caveat there. And then we do ADCS calibration, so attitude, determination, and control calibration. So this is really necessary, particularly for our mission, because our satellites take imagery and we don't want our imagery to be blurry. So that's kind of the next step in our commissioning procedure. And then finally, we start to take images. And as soon as we do that, we proceed into payload commissioning, and essentially our commissioning procedure is done from satellite operations perspective. We also call this first light. So the first time we take a picture and successfully downlink it, we have first light notification, which is always exciting. This is 2 figures of our Flock 4S commissioning, kind of like a timeline, I guess you could say. So what this is it shows each the amount of time that each satellite spent in each phase of commissioning. So again, this has never been shared before, so I'm actually really excited you're the first audience to see this. And if anyone's going to or is going to be tuning into this small sat conference this August, I believe, we are going to be sharing a paper, more details about this as well. But so again, there's these different phases here. So detumbling is in blue, deploying the solar panels, red, purple and green, there's C1 and C2. This just stands for different calibration stages, a part of our attitude, determination, and control phase. And then the orange is from the time from when we completed our attitude, determination, control phase until we take our first image. So I just thought this was a really cool snapshot to see like how each satellite moved through commissioning process. One thing to note is the way that we commissioned our satellites this time was through kind of a batching process. So normally what we do is we choose 5 canaries. Canaries are satellites that we want to go through commissioning first so that we can see if there's any bugs with the commissioning process, and to make sure all those things are ironed out. So it's not totally surprising that you can see I'm sorry if it's too small, but the first 2 satellites, 24-1D and 24-1B, they spent a little bit more time in the commissioning process than the 2 below. And then once we finished commissioning with those first 5 canaries, or at least got through the detumbling phase, that's when we kicked off our batch commissioning, where we started commissioning 15 satellites at once. And every time a satellite finished commissioning, we would then substitute it with another one. So all these satellites are already deployed, but they haven't, started either their detumbling or they're deploying solar panels. That we try to kick that off in batches of 15. And really that's because we only have so many ground stations, and we also have to be cognizant of the other production satellites that we have already in orbit, and we don't want to take resources away from them as well. So we're limited by the number of ground stations we have, and that's why we chose 15, but it ended up being incredibly successful. The length of commissioning for our first 40 satellites. So I mentioned again that we initially deployed 40, and then we had those other 8 in the ion deployer. It only took us 13 days to commission 40 satellites. So 13 days for 40 satellites, which is pretty honestly crazy. I think it's really, really cool. Less than 2 weeks for 40 satellites. And then total length of commissioning. So keeping in mind that we had that sort of 2-week delay for these ion deployer sats, it took 1 month. So I'm just being cognizant of time. I think this is my last slide. Just some really quick stats about the Flock 4S commissioning as well. So it took on average about 4.5 days for a satellite to complete the commissioning process. Our fastest satellite was about 1.25 days to go through commissioning, but our fastest satellite from the time that it began detumbling to the time it took its first image was only 15.5 hours. So that was an incredible achievement on our space ops team. And a lot of it, again, was attributed to the fact that most of our commissioning process, if not all, is automated. So it's really just, queue up a task on a satellite, and after that, it almost takes care of itself essentially. And it's only when there's sort of anomalies or things that are going not as expected that we really need operator intervention. And this is why we're able to speed up this commissioning process so rapidly. And I mentioned this before, but again, we have a 100% record of contacting the satellites within the 24 hours of deploying them from the rocket. So those are some high-level stats. And yeah, with that, I know I talked about 2 very different projects, but I appreciate everyone listening to me. And yeah, if there's any questions at all, I'd be happy to answer them. And I just want to give a shout out, of course, to my satellite operations team, as well as the folks the other engineers I work with at Planet, for being able to have that such a successful commissioning process. And it was really exciting to lead. And at this time, I'll take any questions.
Thank you so much. That was super interesting and impressive. We have a number of questions in the chat. Some are about your career, some are about more technical. Since you ended with more technical, I think maybe I'll go with those first, then we can loop back to career.
Yeah.
One is, what is the altitude of the satellites, which I was quite interested in? And what is the resolution of the images? Are they hyperspectral? And if so, how many bands?
I'll answer with the questions I know won't get me in trouble.
Yeah, I figured.
So they're in low Earth orbit. I mean, also a lot of our information actually about our satellites are on our website. So if you can go to planet.com and kind of sift through that, and that way I know I won't get in trouble with the details I'm giving. So we have 2 kind of classes of satellites as well, right? We have our Super Dove, which are CubeSats, and we also have our SkySats, which are more high resolution. So our Super Doves are around 3-meter imagery resolution, and they're multispectral as well. And our SkySats are closer to 50-centimeter resolution.
There's somebody asking in the beginning about the 25 terabytes that come down per day, which must warrant a huge data processing system. Do you use machine learning to churn through it all?
We personally don't use machine learning at this time for data processing on the amount of data that we get down, but we have started using machine learning in satellite operations to be able to assist with like the relative amount of telemetry that we get from the satellites. I'm trying to see if we can have automatic system to determine whether or not a satellite is essentially like in debugging mode. So we have different modes for our satellites. The two main ones are production and debugging. And these are usually manually updated by operators, but we're trying to use now machine learning to be able to assess based on the health telemetry we've gotten down from the satellites, should the satellite be in the debugging mode or production mode.
Another one, what do you do in ACS calibration?
So that's in our attitude determination and control calibration. So we're basically just trying to calibrate the different subsystem on board. So with respect to like our magnetorquers, making sure that our spacecraft is stable. So we do detumble and get to a certain spin rate, but at the attitude determination control portion of commissioning, we're trying to slow that spin rate down even further and just make sure that we're oriented in a way that our solar panels are facing the correct direction and also that our camera is nadir facing to the Earth.
Good. What is the worst issue you or your colleagues at Planet have to solve?
I definitely can't give details, but everything's been solved thus far, so that's good. I think it's just when, I think for me, a lot of it was the stress of being new as well, like last year, especially when I was starting and being assigned, hey, Kelsey, this spacecraft is kind of acting weird. Can you look into it? And being like, oh my God, if I don't fix this, everything's going to break. And a lot of it was kind of self-induced stress because, yeah, we have a very supportive team, so nothing goes that wrong. But a lot of it at the beginning was more so like, oh my God, I can't believe I'm responsible for these satellites. Like, I don't want to break anything.
So how many people at the company, and do you meet every morning like as a team, or how does that work?
Yeah, so I think we have around 500 folks at Planet. So we're all remote now. Most of my operations team doesn't even actually live in San Francisco anymore. So that's really cool thing about Planet as well, as we're kind of spread out all over the world. And we actually have another Canadian on our team too, based out of Toronto. But we have daily stand-ups, so that's pretty common for, I guess, for tech startups, or if you work in kind of the software space, doing daily stand-ups to kind of assess like, what are you working on? Are there any outstanding issues you need support on? And we also do like weekly syncs with the operations team as well to see if there's like any outstanding anomalies that need to be addressed.
Okay. What is the classification prediction accuracy of the Barefoot? And okay, I'll start with that one.
I can't remember off the top of my head because this was almost a year ago, but I would say it was in the 90th percentile. Like it was pretty high. Yeah.
What is and will be Planet's ConOps for collision avoidance and mitigation?
Yeah, that's a good question. So for the Dove operations, we have CubeSats and we don't have any sort of like thrusters on board. So a lot of it is really just dependent on, working with things like Leo Labs, for example, is one of the collision avoidance space companies out there that will help us like assess the relative risk. But we don't actually have any sort of thrusters to be able to move our CubeSat satellites. But we do have solar panels that, you can adjust the relative angle, and that will, help with phasing or slightly moving the spacecraft. But that's as much as we're able to do with the CubeSats.
By the way, most of these questions are coming with a great presentation. Thanks a lot for all that. Is there a time frame before which detumbling must occur? If yes, how long? About how long is that window?
No, there's no specific time frame. We will get that data down as a part of our like health packets when we get that first contact with the satellites. So if we recognize that satellites are like, there's a particular satellite that's really like spinning in a way that we feel is unsafe, then we can start detumbling right away on that satellite. And we have kind of autonomous systems in place as well to alert us if that is the case. Because again, if there's 40 satellites we just launched, and then we have another 100 that we're normally, operating in general, we rely on those sort of autonomous flags to be able to kick things off, like if detumble rate is too high. But in general, there's no specific time frame. And that's why we're able to do sort of that batching system where we start commissioning 15 satellites and maybe we don't get to the other satellite for maybe a week or something like that.
Okay, do your satellites have the resolution to detect airplanes like the one which was lost at sea in Malaysia?
I would say that probably the SkySats would be more likely than the ones I operate. I'm definitely not an image analysis person or work on like the geospatial team, but the resolution is 50 centimeter, so it's pretty fine resolution, and you can see details of things like ships. Like ship detection is a really big use case for our customers, so I would imagine that planes would also be something that we could see as well.
Let's see, what's it like working with SpaceX as a launch provider?
I mean, only good things, I guess, so far, because our launches have been successful, so that's nice. Yeah, I personally don't really liaise with the contacts there, but I'm happy when they successfully launch our satellites, and it's really cool to be able to like watch our, watch the rocket launch, like ping the satellites and then watch the first stage land. That's definitely very, very cool. I really want to see a launch. My goal is like to see a SpaceX launch that I'm operating for, and then like talk to the satellite after the launch, if that makes sense.
Yeah, cool. For ACS, if you use common filter, are the filter gains constant, pre-designed optimal ones or not? Pretty technical.
That I don't think I can answer, nor do I know how to. So okay. I'll have to pass that, sorry.
Are you worried about the exponential increase in space traffic and the light pollution from satellites?
Yeah, definitely from a space debris perspective, for sure. I mean, mega constellations, it seems like everyone is popping up with them nowadays. So it's definitely a huge concern just in general for just space safety and the health of our just orbits overall, because I mean, I think it was only a couple of weeks ago where we had that rocket part or something was re-entering into Earth, and that was a big worry as well, because we didn't know where it was going to land, if it was going to land in the ocean, who was going to affect. So it's definitely a huge concern. Absolutely.
At some point, there's going to be a major impact between satellites in space, in low Earth orbit. Will that create a cloud that grows until it consumes all of LEO? What with the thousands of new satellites in these orbits, is there a contingency for this scenario?
I hope not, because I'll probably be out of a job if all the satellites explode. I personally don't know if there's a contingency. I mean, in general, the US specifically too, if you're launching satellites, you have to fall within certain regulations for, how long after the end of life of your mission will your satellite naturally deorbit itself based on its elevation or relative altitude. So we do follow those, but in terms of one sort of cataclysmic events, I'm just hoping it doesn't happen or I won't have a job.
I'm going to go to the career questions, unless Omer, you said you had a couple. Are there any technical?
Yeah, they're technical / business. So Samir asked about the Mars rover, and is the sensor wheel the same as the traction wheel? Is it integrated, or is the sensor wheel a separate wheel?
That's a good question. The idea would be that it would be on all, I mean, depending on how many wheels, of course, it would be on all 6 of the chassis. And because it has grousers as well on top of that pressure pad, so it will still have like some sort of grip. But the idea was that it would be integrated into all of the wheels, so that, because of course you saw with the image of Spirit, only one of its wheels got caught, right? So it will be useful if we can have it on all of them. Yeah, that would be kind of the future implementation as far as I'm aware.
Okay, thanks. And then regarding the deorbiting and end of life, so what is the concept of operation for end of life for the Dove and Super Dove series? Do they essentially eventually just fall back to Earth and burn up in the atmosphere? How is that managed?
Mm-hmm. Yeah, so planets are young enough that we haven't really experienced satellites like ending operation and then them actually deorbiting, because they've only been founded since 2010, and a lot of our launches were between 2016 and today. And so for the most part, as far as I'm aware, there's usually for CubeSats in general, it's about a 25-year lifetime, where you just have to ensure that based on where your altitude is or where you're launching to, that you will be able to successfully deorbit. But I haven't actually experienced any active deorbit campaigns or anything like that, because our satellites are still fairly new and most of them are still operating as well.
Okay, thanks. And last question, what is Planet's unique selling proposition? What does it offer that the other companies that provide Earth imaging do not? Is it price, or technology, or a combination?
I'm sure whatever I'll answer, our customer team probably be like, Kelsey, you should have said XYZ. But I think in general, it's the fact that we have the daily cadence of imagery since until I think it's 2009, which is pretty remarkable for 3-meter resolution imagery. And on top of that too, we have a new product, Fusion, where we're able to fuse our data with like Landsat imagery or imagery that's existed for even on the order of almost decades at this point. As well, which is really nice. And that's really powerful for machine learning applications. But yeah, I think a lot of it really comes down to the fact that we have this daily cadence over such a large portion or, of the entire Earth's landmass that makes it attractive, because now you can see this sort of daily change over long periods of time, which is really valuable for assessing like things like agriculture is one of our biggest, if not our biggest use case or business use case as well.
Okay, thanks very much. Those are my questions.
There's a number of questions around your training and, being from Canada, getting a job in the US. So maybe you can answer a few of them at once. One says you've done the bulk of your academic training in Canada. How does it compare to that of your colleagues from abroad? Any advantages or weaknesses?
Mm-hmm. Yeah, I think, it really depends. So our team at Planet and Planet in general is pretty international, actually. So on my team of the San Francisco based team, there's 4 operators and we have a manager, and 2 of our operators are myself, Canadian. Another one is from Toronto. He lives in Toronto, Canadian, and the 2 other are American. So that's always like a kind of nice sigh of relief of like, oh, I can work in the space industry, even though I'm, a Canadian, especially in the US space industry as well, because it is quite rare, a lot of restrictions. I'm sure all of you have heard of ITAR, or at some point, if you've been kind of applying to places, ITAR is a huge restriction. Or just they want US citizens. In terms of my academic background, I think one thing at Planet specifically is they do implement like blind screening to the university you went to. From my understanding, like just from friends and colleagues, that a lot of aerospace companies, they want the Big 10 aerospace companies from the US, or sorry, the Big 10 aerospace universities, which I don't even know what they are. But Planet tries to avoid doing that, which is nice. So we have people from, even I think our director of onboard software, he is Canadian as well. He went to Queen's. So yeah, there's definitely a strong Canadian presence at Planet for sure. And yeah, I wouldn't count yourself out or anything just because you don't have an American degree, especially for the relative cost. It definitely is something to consider as well.
And I know you mentioned your time in France as being pretty instrumental. So somebody's asking which internship or which piece, or is it a combination of pieces that allowed you to get into this industry, do you think?
Yeah, it's definitely a combination. It really feels like almost a snowball effect, and it's a mixture of like definitely hard work and perseverance, and also luck and right place at right time, and just like opportunities snowballing. It's really just like a conglomerate of those things. Sorry about the sirens. I live in the city, so you can hear that. For me, for the Paris internship specifically, they were just incredibly supportive, and they're almost like family at this point than just strictly colleagues. So I was just incredibly lucky with the people I got to work with, and that they were really supportive of just my interests and what I wanted to explore. And like, I honestly emailed them and asked, can I do an internship there? And they said yes. Like, it was no formal real like application process. I had done a 1-week summer school before. And then I thought, this is really cool. I want to live in Paris for a summer. Like, why not? I'll just kind of reach out and see what happens. So the fact that they even, took a chance on someone that had no sort of space weather experience was fantastic. And yeah, I think it's just a combination of things snowballing too. And that I put myself out there. I apply to basically any and every opportunity I can. And that's why I have a very diverse experience, because I just figured space is cool. I want to work in space. Let's do rover stuff. Let's do space weather stuff. Let's do, sat op stuff. So that's kind of, I haven't really found like a specific niche. And I think that's been lucky in that now I've kind of have all the skills are transferable across my experience, whether or not they're like directly related technology wise. So I think that's been valuable. I hope I answered
What was
that.
your master's degree? What was your master's degree on?
Yeah, so it was in machine learning classification of interplanetary coronal mass ejection storms. So essentially using satellite accelerometers to see if we could detect coronal mass ejection storms, which are essentially really big explosions on the surface of the sun. So this is kind of how my thesis transformed from that one summer internship at Paris, where I knew nothing about space weather. I came back and said, like, maybe I could do a thesis on this where I can combine, you know, what I learned in the summer to the computer engineering degree I'm doing now. And that's kind of how it formed. And then I learned more about machine learning, and that's how I got into JPL. And then I learned more about coding, and that's how I was able to kind of pass the different tests I had to do to get into Planet. And so it kind of just snowballs.
Very cool, very cool. And Oxford, you're going to be doing that online, or?
No, I'm moving there, and I just booked my flight like yesterday or the day before. So I'll be moving there in September. Yeah, so it's quite a small cohort, which is nice. There's only about 10 to 15 people a part of the program every year. So I'm hoping things will be in person if we can do it safely. But yeah, headed over there.
You're going to keep working at Planet, or?
Yes.
If I may ask.
Yeah, so I'm planning on working as a part-time and full-time PhD. So we'll see how that goes.
Cool. I think that covers a lot of the questions. If anybody have any burning questions, maybe you can re-put them in the. Do you work with different engineers in your field, chemical, electrical, mechanical? I guess that's yes.
Yeah, definitely. I mean, I work with because you have to, when you think about a spacecraft, it has so many different subsystems, and we have a team dedicated to each one. So I work with like our attitude determination control subsystem, our onboard software, our, you know, RF and antenna design, thermal. We work with, especially in satellite operations, because if there's any sort of like changes in a subsystem from the previous build, that might affect how we operate the satellites or what we should be looking for when we're looking at their telemetry. So I work with all of them, mechanical systems.
Great. Well, I'll read one that's representative of many. It says, Kelsey, you're an inspiration. What you've done and worked on is exceptionally cool. And I wish you all the best in your endeavors. Cheers.
Oh, that's so nice. Thank you.
Thank you so much. I'm going to pass it over to Omar.
Yeah, cheers to that last comment for sure. Catherine, thank you so much for expertly moderating the Q&A session. Kelsey, that was a wonderful presentation, a great story of your career arc from Carleton to JPL to Planet and then off to Oxford. So really exciting. And thank you to all the participants as well. I counted 74 at one point. That's just a great turnout. So thank you everyone for your interest and your questions. Kelsey, on behalf of CASI Ottawa branch, we'd like to offer you a thank you gift. I love aviation and space biographies, so we're offering a choice of 3. So one is Kelly Johnson's biography. He was the chief engineer at Skunkworks, and his approach to engineering and design and management is legendary. The second choice is Elsie McGill's biography, Queen of the Hurricanes. She was responsible for hurricane production during the Second World War and Canada's first aerospace engineer. And then the third option, I don't have a copy with me, is Michael Collins' biography, Carrying the Fire, which is about the Apollo 11 mission, which is a great read. He passed away sadly recently, but just an amazing story. We can discuss, but which one you prefer, and we'll get that shipped out to you. And if there's another option you prefer, we can also discuss that. So, but thank you on behalf of Catherine, my co-host, and myself and CASI Ottawa branch. Thank you so much. That was a wonderful presentation, and looking forward to keeping in touch. So.
Yeah, thanks so much for having me. I really appreciate it. And thanks everyone for the great questions. And yeah, I realized I didn't leave any contact information on my slide. I apologize, but I can maybe write it in the chat or something like that if anyone wants to reach out.
Super.
Yeah.
Thanks so much.
And CASI can share as well, via the email that we. Okay, thanks everyone. Cheers.